Hi, so my name is Bruno. I'm a concrete engineer at Kiewit in Denver, Colorado. Concrete engineer is a bit of a very broad title. More specifically and practically, I think a better title would be concrete wizard. And it being Halloween, I brought a little wizard hat. Concrete wizard, because some of the things that I get asked to solve is what happens when my concrete is not meeting strength, it's not setting, or it's just they placed it upside down. Whatever you have. Kiewit's a large construction company all over North America, and we pour a lot of concrete, and there's a lot of problems with it sometimes. Also, it being Halloween, I brought some candy. So if you're looking at your phone, you might want to look up, because there's candy coming your way. So, yeah, have at it. And you can pass this back that side. I'll take this off. And then you can pass it this side. So, one of these wizard tricks that we get asked to do, I specifically get asked to do, is how do you guarantee that a building's going to last 100 years? That's one of the new things that's really hot in the industry. People want 100-year service life. There's sustainability reasons, resiliency reasons, and economic factors as well. If your building lasts 100 years, that means that, per unit year, you are making a very sustainably structure just by virtue of reducing the maintenance cost and repair down the road. And basically, when we say that it's going to last 100 years, we are talking about protecting it from chloride-induced corrosion. On the right is just a very simple chloride corrosion model of when initiation happens, when damage happens, cracking, propagation, and eventual collapse. The challenge is that there's no real specific design guideline or specification on how to get to 100 years. This is where the wizardry comes in. Lack of standardization. In ACI, there are committees where we're trying to figure out this right now. So I highlight that one. We're also just, like I said, focusing on chlorides. And these are some of the other multiple variables and factors, namely availability of materials. A lot of sessions on new materials that are coming up and how they're changing for other reasons, but they also obviously affect durability. This is just a very brief overview of how corrosion works. You have an exposure to the sodium chloride solution, seawater, de-icing salts, and then your chlorides from that solution are penetrating into your concrete. The rate at which they ingress is based on your permeability. Eventually, you get enough of them in there, your steel reaches a threshold, a limit at which corrosion initiates. Rust products, which are expansive, create a pressure, inside pressure, create cracks, and so on. So we don't want that. So what we do is we model the service life by using a couple of parameters, namely permeability, which quantifies the resistance to fluid penetration. These are a couple of the tests that we do. They're fairly short tests, 1 to 3 months. We also get another parameter, aging exponent, which is modeling how fast permeability is dropping. So permeability and how fast it drops. These are some of the other tests that we do. These two parameters are mostly influenced by cementitious materials, water-cement ratio, and the percent replacement of those cementitious materials, like your fly ash or your slag. I'm going to be focusing on these two, migration, I'm going to say migration a million times, and resistivity. And as if you weren't confused before, I'm also going to talk about conductivity, which is the inverse of resistivity. But don't worry, I got some useful arrows for you to keep track of things. So, because I'm going to be talking about permeability and conductivity and resistivity and all the ivities, I'm just going to put arrows showing down is good or up is good, so you can keep track of it. This is typically how permeability tracks with time for concrete as you develop strength, as the matrix hydrates and hydration products are forming, your permeability is going down with time. We're in the scale early on of months, eventually years, but in general, this relationship follows a power law function with an aging exponent right there, K. I'm going to be referring to it as alpha a lot. We get to this relationship by doing a few tests at 28, 56, and 90 days, and then pretending that because I get to 90 days, I can predict 100 years, which is a stretch. This is basically showing you, again, I can get these 3 points, and then mathematically, I'm going to get the rest of the line. I do migration at 28 days, and so on. This is what a default plot looks like for 3 materials: straight cement, fly ash, and slag. And again, good is down. So you can see that green, the fly ash, is the one that goes the lowest. We see that these alpha values are between 0.3 and 0.6. The higher the alpha value, the more it's going to go down. It's an exponent. It acts up really fast, but again, it takes a couple of years for it to get to a more final section. We see that fly ash is more effective than slag, which is more effective than OPC. It's an exponent. There's a rapid decay. Takes years, but we really pretend that we know what we're talking about at 90 days, which is 0.25% of 100 years. So that was a little bit of background on permeability. Hopefully you guys are the experts by now after that. And I have data from a few case studies, 3 projects that three very real projects, 1 on the West Coast, 2 on the East Coast, dealing with fly ashes and dealing with slags, type 1, 2. Don't even touch 1Ls. Again, things are changing very rapidly. A couple of notes. These are what I would consider mega projects. The scopes are in the billions, which means that there's an extraordinary level of oversight and resources on these projects. The data is very recent, within the last 2 years, and this just gives you an idea of when we do these operations, we have half a dozen technicians, we have tents, we have curing boxes. We're doing the best that you can do in an industry, in a job setting. No one else outside of research can take this much care of cylinders when you have such big jobs. We have reputable labs involved that I've personally inspected. We have the proper sampling, the proper storage. We check for outliers in the data. When we get funny numbers, we send them to 2 different labs to validate them. On the right, this is showing you one of these trials. I wrote that just to tell the lab, these cylinders go here, these cylinders go here, separate them, label them. Again, I care a lot about these cylinders. The people there care a lot about this. They get paid to care for the cylinders. This is as good as it's going to get in the industry. This is what the test matrix typically looks like when we do these marine concrete mixes that need a 100-year service life. One mix can take 3 to 6 months to qualify. It's about 100 samples, beams, cubes, well, not really cubes, but cylinders, beams. It's about $50,000+ of testing. There's lab and field settings. We have to use multiple labs, which involves shipping cylinders all over the country. Typically, we use different labs because if you look at these tests, they're very high-end for industry, RCPT, migration, resistivity, hardened air. So not every lab in the country uses that. And we use the local lab for your mechanical properties, your strengths, your elastic modulus, your tensile stuff, the boring stuff. So part 1 of the first cases that I have is when things make sense. And when things make sense, they're still challenging, but at least they make sense. This is from the first project where we use fly ash. And we see some very, very key takeaways that are logical. The more fly ash you use, the higher your alpha value, 0.8 with 45, 0.64 with 20%. Awesome. We see that water cement ratio is affecting your early permeability. That's logical. High water cement ratio, high permeability, and so on. But we are getting high values of alpha. Previously I mentioned 0.3 to 0.6, and now we're getting 0.8. So that's way better than I thought. So I figured question comes up, should alpha be capped? So should we be conservative and say this concrete's not this turbo, it's a little slower? Maybe I thought, okay, 90 days is very early. What if we run these samples to a year? And because this is such a mega project and I can spend money left and right on testing, I was able to do testing up to a year, which is very rare in any construction project. So I actually ran them for a year and I got a higher alpha value. So maybe not. Maybe alpha shouldn't be capped at 0.6. Maybe we can go to 0.8, 1.1. Another question came up. When should alpha be determined? Because I just told you 90 days give me a different number from 1 year. So this is what happens. The green line is what is my permeability if I just think that 90 days is correct. The blue is I measured it and it got better. And then the orange is I measured it and it flattened. And you can see there's a huge discrepancy here on what my alpha can be. So I'm calling this Schrödinger's agent coefficient. If I don't measure it, I don't know. If I measure it, could be better, could be worse, I don't know. 1 year, I did a bunch of retesting and I found great correlation at 1 year that was not present in 90 days. If there are any researchers here, you know that when you get 2 decimals of similarity, you right away are like, that can't be right. And I ran the numbers like 10 times, and they were right. And they were right for 2 other sets of mixes. So this shows that at 1 year, this fly ash was super consistent. I mean, this is mock-ups in the field and in the lab halfway across the country. This was just remarkable to be able to match these results. And I did check that it was not the same set of data. So again, this is saying fly ash is great. And if you measure it for a year, I think you have really consistent, reliable data. So you may have noticed I'm going to bring up more questions and answers throughout the presentation. This is from part 1. Part 2 is what happens when things stop making sense. This is from the second project, which involved slag. 2 years ago, I started doing lab trials with these mixes. We did production trials, we did mock-ups, we started doing placement. And right away, we know that with the slag, the resistivity was just awful. These lines are super flat by mathematical standards, which are giving me these just god-awful alphas. I mean, you remember I was talking about 0.3 to 0.6. I started with 0.11, and I barely got to 0.3. So this is behaving like an OPC, seemingly behaving like an OPC. And I also found that 90 days was about the same as 9 months, so it was not a time issue. And at the time, these were, what I'm going to say, unremarkable, but good enough numbers because the service life model worked. So I didn't like them, but it was good enough, so we moved on. And the problems arose when we moved on to construction. We had this baseline during lab trials, production trials of resistivity, and we had a QC limit of like, okay, for our durability to be there, we should not be below this limit. We did mock-ups. Months later, mock-ups were better. That's awesome, no problems. And then the second we went into construction, we dipped below the non-conformity level. So that raised all sorts of flags, and people started getting worried, and I get calls about what the heck, how do I explain that? And I started digging into it little by little. And by the time that we were able to get more information, things got better magically. And then the project wanted to move on, didn't care. I didn't get to do my science fair experiment, but that's what basically was the inception of this presentation, that what the heck is this? How do we explain this? I can't. We saw that the trend for resistivity matched at 28, at 56, and 90 days. So we know for sure that something was going on with this concrete that made it have low resistivity consistently. We compared it with strength. In broad terms, durability is not the same as strength, but good durability should also come with good strength. And we saw that sometimes your low compressive breaks have good resistivities. So that was not even matching. There may be some drops in strength because of seasonal effects, water demand in the hotter months, and so on. But in any case, no real correlation with strength. That was the key aspect. And we also see that strengths did not see the big dip that we saw in resistivity. We never had non-compliant strength. Strength wasn't an issue. It was just the resistivity. This is a very valuable slide because this is a bunch of alphas tracked with time. So each of these data points is 3 resistivities up to 90 days. Again, I showed that early on we were not great. It was kind of like in the 0.3 range. And then when we moved to production, things got funny. But the literature will tell you slag should be around this line, and instead it was just like that. I mean, this is just noise in the data. So a big topic that's happening in the service life committee is what's the difference between your design service life and your as-built service life. And this would tell you abysmal, because every time you drop below 0.3, you're probably failing your service life. So questions are, what caused resistivity to fluctuate, and is resistivity accurately measuring permeability for these slag mixes? So with this in mind, we had to do something new, so we had some new ideas. The first one is, what if we just do a bunch of different measurements at different temperatures, if we accelerate it? So we put resistivity samples at 23 for 7 days, and then at 38C, and we found that we were basically trying to predict the future. So maybe you can get 150-day results in 90 days and so on. And you can also get a bunch of new alphas because you have new lines. And you can find when the pozzolanic reaction from the slag flattens. In general, that was promising, but we still had these low alpha values, and there was a lot of variability. I'm just showing you the plots that look kind of nice. The other idea was that we were just going to do a bunch of different testing, migration, resistivity, and RCPT, and compare 3 different types of alphas with these. We found a big disconnect between migration and resistivity. You see these are 2 axes on the left, conductivity on the right, migration. And because they're measuring permeability, they should be sort of on the same line or showing the same trend, but yet they don't. We have this huge discrepancy where migration is actually showing that OPC is pozzolanic. That's this big drop right here. So big discrepancy there. Something interesting, we see that there's a parallel trend between migration and resistivity, but it takes 56 days. So something about resistivity didn't capture this drop. And just a reality check, why is OPC behaving pozzolanically? We do see, the 4th takeaway is that there is agreement between conductivity and RCPT, which are both electrical methods. So that kind of hints at something going on with electrical methods. And in general, we see a wide variation between alphas, aging coefficients, and which test you do. And this is a very real question that we're facing. You have 3 tests measuring the same property, giving you 3 different answers in different directions. This 0.29 is sort of close to this 0.22, so I kind of say, they're close to each other, but they're low. Migration is more in line with what I would expect, so I like that number better. But again, you see even OPC can be in the 0.7 range. So part 3 questions are, how do you assess variable performance with different tests? How should aging coefficients be determined, and what should the QC criteria be? So in summary, I have actual just questions. Should alpha be capped? I'll mention that Life 365 capped at a 0.6, but we saw that maybe these are from older materials, so we can do better. When should alpha be determined? FIB says 2 years. What caused these values to fluctuate? I don't know for sure, but I think it's a change in the slag. The ASTM specs for cementitious materials don't focus on durability, they focus on strength. I think there's a compatibility issue between testing and materials, namely with electrical methods and the slag. Research needed to address different performance, research needed for how to really measure aging coefficient, and what should the field QC criteria be. I think maybe we should drop resistivity, focus on migration, and do it less frequently. References, and then questions. Happy to take questions, but also answers from you guys, because I don't know this. Experts in the field don't know it either, so we could use new ideas. Thank you.